Today I want to start with telling you, uh, explaining to you one of the experiments that are commonly done in fracture mechanics to calculate critical energy release rate. The experiment is called double cantilever beam. Basically, if you think about it, it's this specimen has an initial crack that has a length of A, okay? And a force P and P, pair of forces, P and P, are applied symmetrically. And the crack opens up. So we have a displacement delta and crack P. So prior to any crack growth, we can say that the delta, the displacement, is equal to C times P, where C is the compliance of the beam. And so a comparable or a similar geometry is drawn here, in which if you want to do the experiment, the fracture mechanics experiment, you will apply a pair of forces, P and P here. And at some point when P here or P there reaches a critical value, the crack will start growing. The critical P has enough information, and after you know the geometry, you measure the geometry, has the information you need to calculate the critical energy release rate. And this is what I'm going to do for you. And at the end, I tell you why this is not the best experiment to, as you see here, not the best experiment for self-healing. So in order to do that, let me share with you my whiteboard. So imagine this is one of the beams. This is the other one. So basically, the rest of it, so from here to here, is basically A. Okay, and two forces are applied here. One is this P, and then the other one, this P. And as a result of these two forces, I'm going to show each beam based on the center line of the beam. As a result of these two forces, the beams will deform like this. And here there's P and there is P. And as we said earlier, so in this case, you can easily show that delta is equal to C times P. This is the definition of compliance. And from beam theory, I can show that the compliance is proportional to the ratio of A over H to the power of 3, where H in this case is actually this. So it's the height of each beam. Now, what you can see from here is that if H is the more the H, the lower the compliance, which means the beam is stiffer as expected. But the longer the beam, we also see that the beams become more compliant. Basically, basically, as crack grows, the guy becomes more and more compliant. So now, the energy stored in the energy stored in the material during this loading prior to any crack growth, I call it UE, which is the elastic energy, is going to be 1 over 2 P times delta, which is 1 over 2 C times P squared. Okay, now if the crack grows by delta A by a small increment, and let's say I keep the force constant, it's a force-controlled experiment, then the elastic energy will change by some amount, which I can show with this. oops, sorry. Let me, right? Now, if the crack grows by delta A, I am also, so basically, as the crack grows, some elastic energy in the material will be released. And so that energy has to go into breaking the bonds. And the energy that it takes to break the bonds, I can show it by GC, and this is actually G1C, times B, the width of the beams, times delta A. This is delta of area. This is the new area that is generated. And so then if I set that, this equal to 1 over 2 P2 dC dA delta A, this delta A and this delta A go away with each other, and I get this is equal to P2 dC dA divided by B, right? Now, here's the problem. Now I go back to my slides, and so this is the equation I wanted to put there. But because I know how C changes with because I know how C changes with A that we derived, we showed here in this point. Now I can go back to my slides and I can get some interesting conclusions. Basically, GC becomes this value where beta is the proportionality constant. So this, please correct this equation. This has to be, there's no equal. C is proportional to alpha over H. And so GC, the proportionality constant, I call it beta. And so when you put, instead of dCdA, you put its value based on this proportionality, you get this equation. Now, GC is a material property, which means when A goes up, in order for the crack to grow stably, P has to go down. GC is a material property, so this is a constant. So when your P reaches the critical value that the crack grows, as the crack grows, P has to drop to maintain this equality, which means if you don't drop P, the crack will go from this to open completely. Okay, so now, and that's a problem in self-healing experiments, because in self-healing experiments, you want to have a stable crack growth, gradually stable, so that you can put the two pieces together again and start the experiment and do the healing and start the experiment. That is why, and how can you do it? Well, if as A goes up, H also goes up, then you can have a stable crack growth with some equations. But without going into the math, I show you the final answer, which is an experiment that is this. It's tapered double cantilever. So in this case, as the crack grows, so let's say the crack goes from here to here. When it goes from here to there, the height of the beam also goes up. Now, deriving the right shape is, or the right dimensions requires further math that we're not going to get into, but at least you now understand why most of the experiments in self-healing are like that. So I'm going to stop this video here and continue in the next.